Hi everybody, Matt Morgan. In this lesson we're going to work Wiley Problem 12-22, a problem that involves dimensional analysis and calculating parts per billion. Here's the problem. The maximum allowable level of a certain metal in drinking water is 35 parts per billion. What mass of this metal in milligrams is allowed in 5,000 gallons of drinking water? They also say assume that the density of drinking water is the same as that of pure water, and they want their answer in milligrams. In the Chapter 12 lesson, we discussed calculating parts per million and parts per billion. This problem gives us a parts per billion and has us calculate the mass of the dissolved solute. The formula that we discussed in that lesson: parts per billion is mass of solute over mass of solution times 10 to the 9th. Now the answer box lists milligrams, so we're going to have to express our mass of solution in milligrams. One point that we brought up in that previous lecture is that both the masses of the solute and the mass of solution have to have the same units. We will use the given parts per billion, convert 5,000 gallons to milligrams, and then solve for that mass of metal. I think the most challenging part of this whole problem is that conversion of 5,000 gallons to milligrams. We did dimensional analysis way back in Chem 1, and we're going to have to use those skills again to make this conversion. We're going to need the density to go from volume gallons to milligrams, and they tell us that we assume that the density of this drinking water is the same as pure water. We're going to use 1 gram per milliliter for that conversion. Let's set up our dimensional analysis grid. Our given information is 5,000 gallons. The target unit is milligrams. We start with 5,000 gallons. There are different ways to do this conversion. The way I choose is first to convert the gallons to liters. That conversion is 1 gallon equals 3.785 liters. Now you won't have to memorize this. If this problem is given on an assessment, you will be given that conversion. But we do have to put gallons on the bottom and the 3.785 liters on the top. We will cancel our units here once we've put everything down. The next step is to convert from liters to milliliters. You should know that the conversion is 1,000 milliliters equals 1 liter. We put liter on the bottom, so it cancels with liters on the top from the previous conversion. The next conversion will be from milliliters to grams. Here's where we use our density. 1 gram over 1 milliliter, once again, to get the volume to cancel. Our final conversion is we're going to convert from grams to milligrams. Once again, this is a conversion you should have memorized. 1,000 milligrams equals 1 gram. Now before we deal with our numbers, let's look at our units. Gallons cancel, liters cancel, milliliters cancel, and finally grams cancel. We are left with our target unit of milligrams. Numbers on the top get multiplied, numbers on the bottom get divided. All the numbers on the bottom are 1, so that should be pretty easy. Go ahead and calculate this number. I'll pause for a couple minutes, and of course you can pause the video as well. Don't trust my numbers, see for yourself. I get 1.8925 times 10 to the 10th milligrams. That's a really big number, but milligrams is really small, and 5,000 gallons is quite a bit of water. So that passes our common sense test as well. So that is the number we're going to put for our mass of solution. There's our problem again. Now what we need is to plug in and solve for our mass of solute. We have every other value that we need. Here's our formula again. We will plug in 35 for our parts per billion. We'll plug in the value we calculated on the previous slide for our mass of solution. Now we have one equation and one unknown. We're going to do some algebra. Isolating that massive solute will require us to multiply by 1.8925 times 10 to the 10th. We will divide by 1 times 10 to the 9th. Go ahead and do that calculation. I get 662.375 milligrams. Now we've carried extra digits through, but based on our given information, we will express our final answer using two significant figures. We can say 6.6 times 10 to the 2 milligrams. If we want to put that into Wiley, we can say 6.6 E2, or if you just want to put in 660. That is the answer to our problem. So we worked a problem. It combined dimensional analysis, great review, with calculating parts per billion. As always, if you have questions on this problem or any other, contact your course mentor. The main job of your course mentors is to enable your success in these courses. You can email us at the group inbox at chemistry@wgu.edu, or you will find contact information for your individual course mentor in your course of study.